Hello there. We're headed for more distant ground this time. We've learned how to differentiate a little bit faster than the last time around with some power rules for you. Now we're going to move on to something a little bit different. Not too different. It's still calculus. Rates are changed, so you know we're talking about calculus. Two particular examples we're going to use are velocity and marginals. And so I threw some graphics in here at the top. At the bottom, since it just says marginals, and you don't know what they represent, I'm going to throw in something really quickly here. Before I do that, I'm going to see if I can connect the pen here. Where's my pen? There we go. Activate the pen, and here we go. So we've got three marginals here, and you don't know what marginals are yet, perhaps. At least I wouldn't expect so. Before I taught business calculus, I had no idea what these things were. Marginal revenue, marginal cost, marginal profit. Actually, as they occur in real life, cost probably comes first, but this is the way I like to think of them. First, the money comes in, you pay some things like the rent and so on, and then if there's something left over, there's your profit. Now, the marginal part is the different part. The marginal part means, for example, for the revenue, if you sell one more item, how much more money are you going to have coming in? For the cost, if you sell one more item, how much is it going to cost extra as it costs you to have one more TV set in your store? And last of all, if you sell one more item, how many dollars do you expect to make? Very important if you're going to go to Acapulco or somewhere for your vacation, for the summer, or wherever you want to go. So let's look at some other things first to set this up. First of all, there's two different kinds of speed. You're familiar, most of you at least, I would expect, with the speedometer in your car. That's what shows you what the instantaneous speed is. Now the difference is, when you look down at the speedometer, now this one isn't going anywhere, so I'm guessing this is a parked car. What you don't get there is what your speed is for an entire trip. This tells you how fast you're going in any particular instant. So if maybe you're pushing things just a little bit and there's a red light flashing in your rear view mirror, that might mean your instantaneous speed was a little bit high. Now, what am I talking about? Let's suppose you were going to make a trip this afternoon to Charlotte and back. So you start here at mile marker, say 75. Head for Charlotte. You get there an hour and a half later, and if it's 75 miles away, that means you've averaged 50 miles an hour. The two things that are involved with that speed are how far did you go, how long did it take you. Divide the two, you get your average speed. Now if you do get there in an hour and a half, going with 75 miles, that means you've averaged 50 miles an hour. Does that mean that you won't see that red flashing light in your rearview mirror? Well, maybe not. Because at the very beginning, maybe you're going 0 at the beginning of your trip. Maybe getting on the on-ramp, you're going about 35 miles an hour. That's different. When you're in cruising speed, maybe you're going 70. But at the end of the trip, you compare your distance and your time, and you've averaged 50. But maybe at some point you were going like 75 or 80. And that's possible. Because some of those times you might be behind some slow traffic, and you're only going 35, 40, 50 miles an hour. The average speed and the instantaneous speed are something different. The instantaneous is what you see on your speedometer. The average speed, how do you figure that? Well, on the left you can see your stopwatch. That's going to help you figure out how long you've been on the road, and your odometer, if you subtract what it was at the end of the trip when you got to Charlotte minus what the odometer said when you started in Spartanburg, that'll tell you how far you went. Divide the two and you've got your average speed. The difference is that you've got a time interval. The thing you're dividing by, you found by subtracting two different values of time. You've got a time interval, so you've got average speed. That does not mean that when you passed Gaffney, you were going exactly 50 miles an hour. You might have been going, let's hope not, but you could have been going 100 miles an hour. Or you could have been going 20 miles an hour in a traffic jam. Those are instantaneous speeds. The average speed is for the entire trip. What did you average? So these are some of the things we're going to talk about. And here we go. Average rate of change. Remember, this is over a certain amount of time or something similar to that. That's an easy way to remember it. Distance over time. They're both intervals. So we've looked at two applications of intervals, slope and rate of change. The slope and rate of change you've both worked with before. A little bit different in calculus, but not too different. One of the things you want to remember today after finishing up is the difference between the average and the instantaneous rate of change. Instantaneous means how are things changing right now. Average means over a certain period of time, maybe 2 hours, 3 hours. What are you averaging? Over that time, you'll have various instantaneous rates. This is what you've got for the average. Next, you want to distinguish between those two and be able to do either one. The average one, the average rate, will involve a secant line. If you think of a secant in a circle, remember a circle, of course you know it looks like this. A secant line cuts through it and hits it at 2 points. You would take those 2 points, the coordinates associated with them, and calculate your average rate of change. The actual tangent line at that point, let's take this point over here, the tangent line of this point would tell you what the slope is at that exact point, which would be a little bit different from if we went through that point and another one creating a secant. This slope would not be the same as the slope of that line. The tangent line will give you an instantaneous slope. The secant line will give you an average slope. Here's the definition of the average rate of change. If you look in the middle here, where we've got this rectangle, notice that on the top we've got two y values. I know it says f, but f represents just some function. So you could write it sort of this way. What's the y value if x is a b? What's the y value if the x value is an a? Those are the function values. Those might be distances, for example. On the bottom, you have the original values before you gave them to the function. So b minus a. Functionally on the graph, notice that a is on the left and the b is on the right. When you want to find out what the change in x is, you take the second one minus the first one. If you want to find out what the change in y is, you take the second value of the function minus the first value of the function. This will give the average. And it's the average because this does not need to be 0 or even close to 0 to get the average. You have a right endpoint and a left endpoint. A to B is what your x values are doing, and y from the A to the y from the B, sort of, if that makes sense to you. So here is the average velocity. Where's my pen? There we go. Average velocity. So on the top, you're going to be subtracting where you end up, so we'll call this final distance, from, let's say it's a distance from Atlanta on Interstate 85, minus the distance from Atlanta when you started. What do we divide that? That's the change in the distance. We're going to use Atlanta as our basis, so for our origin for Interstate 85. I know it doesn't start there, but we'll just use it. You can use anything you like. On the bottom, if you look at your watch, now your watch isn't a stopwatch, so for the second one, you look at what your watch says when you get to your destination, minus what your watch said initially or when you started. And that gives you your average velocity. Now here's an example. I'll try to take you through this pretty nicely. First of all, we're talking about something falling from some height. Imagine going out on one of these buildings, say in front of the main building, looking up at the top. It would be interesting to drop a baseball from the top and see what happens. So let's suppose Maine is about 100 feet high. Probably exaggerated, but we don't care for right now. This distance S represents the height of the baseball after you dropped it. The T represents how long it's been since you dropped the baseball. 100 represents how high the baseball was before you let it go. So this formula, I'm going to write S this way, it's a little safer. S equals minus 16 t squared plus 100. So at time 0, before you let go of the baseball, this minus 16t squared is 0, and the height of the baseball is 100 feet. Of course, you're at the top of the main hall. 1 second later, what happens? Well, how high is the baseball? Exactly 1 second after you let it go. Put the 1 in where the t is, do a little bit of calculation. This is going to be a negative value, add it to the 100, and of course what's happening is 1 second after you let go of the baseball, it's not going to be 100 feet above the ground anymore. This negative sign right here means we're going to be subtracting a number. So maybe 1 second later it'll be about 84 feet above the ground. So what we're going to do is we're going to find the average velocity. Remember, that's over a certain period of time, over each interval. We're going to choose our intervals. We're not actually going to go up on top of a 100-foot building and drop a baseball. Someone might be walking below. But we're going to look at what the average velocity, and you could write it this way. V for velocity. You usually put a line right over the top. That represents average. Not to be mistaken for just the V. The V itself would be instantaneous velocity. This represents average velocity. So you're going from the 1 second point to the 2 second point. What is the average velocity if you go from 1 second to 2 seconds? That's what we're interested in. The second one, we're going to be looking for the average velocity as we go from 1 second to 1.5 seconds. Now, we can tell how we're going to calculate the time part, the part that goes in the denominator. For this first one, for example, in the denominator we'll have 2 minus 1. That'll give us a 1 second interval. The second one will be at 1.5 minus 1. We've got a half second interval. And the third one, 1.1 minus 1, is a 1/10 of a second interval. But what distance has the ball actually traveled, or whatever it is we're dropping? Well, we have a formula up here, and this can tell us where the ball is at any particular time. So here we go. Someone's done a little bit of that work for us. Here's our formula up on top. Where's my pen? Here's the formula on top. We've got several different values for time. And all you need to do is take each one of those, put it in your formula up here, and you'll find out how far or where that object is at those 5 times. Someone's already done the work for us. 0 seconds, it's still 100 feet in the air. After 1 second, it's still 84 feet in the air. After 1.1, it's 80.64 feet in the air, 64, and 36. Now, if you've got that, for the interval 1 to 2, 1 second to 2 seconds, at 2 seconds, where's my pen? 2 seconds, there we go. At 2 seconds, it was 36 feet in the air. At 1 second, it was 84 feet in the air. You're going to be subtracting them. Remember, second minus first. Which came first? The second one goes first. The first one goes last. Same thing on the bottom. 2 seconds minus 1 second. The 1 happened first. 2 happened second. Double check yourself. The 36 feet and the 2 seconds are an ordered pair. The 84 and the 1 are an ordered pair. You're in good shape. A little bit of calculation, and what do we get? Negative 48, or negative 48 feet per second. Remember, we were finding the average speed over that interval from 1 second to 2 seconds. We don't care what happened from the time you dropped the ball. It's what happened, what was the average speed between 1 second and 2 seconds. Second, we've got a different interval, a little bit of a closer one, from 1 second to 1.5. If you look over here, the 64 represents 64 feet in the air at the 1.5 second checkpoint. The 84 represents the height of that object at the 1 second point. Subtract the time values. Remember, 64 and 1.5 go together, 84 and 1 to go together. Do your arithmetic. There are your numbers to the division, and there's your average velocity from 1. Remember, it's the average velocity going from 1 second on your watch to 1.5 seconds on your watch. Next, for the interval 1 to 1.1. All of these start at 1 second, but they end at different places. For this one, on the bottom, take the easy one. The 1.1 second comes second, so we subtract that minus the first time. Second, we'll get the distance values, 80.64 minus 84. Notice again, the 80.64 and the 1.1 go together, the 84 and the 1 go together. We're ready to do a little bit of arithmetic. There we go with the subtractions. And this tells us that from 1 to 1.1 seconds after you let go of the baseball, or whatever it is you choose to drop, the average speed is negative 33.6 feet per second. Remember, that's average rate of speed. You've got an interval of time. That's the key, the interval of time, and that goes in the denominator, as opposed to the instantaneous. Now we're really talking calculus. So let's take our time interval from 0 to 1 second. We want to find out what the speed is, the instantaneous speed. Where's my pen? There we go. We want the instantaneous rate of change at t equals 1. So we take 1, and what we found was between 0 and 1, the average speed was negative 48 feet per second. From 0.5 seconds, or 0 to 0.5 seconds, the average speed was negative 40. From 0 to 0.1, the average speed was negative 33.6. And getting closer and closer to 0, there's the average speed over that interval. It approaches negative 32. But of course we can't divide by 0. That's where the calculus comes in. That's why we have calculus defined from a limit. It enables us to do something that we wouldn't be able to do otherwise. Unfortunately, in the last section, we actually made that definition a little bit easier to work with some special rules that we have for calculus. This is how it's defined. We saw this in 2.1. Here's our time interval. We can use that to find the average rate. And what we'll do to get the instantaneous speed is let that delta x, alias h, get closer and closer and closer to 0. Remember, h is positive. So this is what we do. We take the limit as that delta x approaches 0. So our 2 points that have x coordinates of x and x plus h get closer and closer and closer together. So the secant that we've got, let's draw a little circle out here. So the secant we've got, not very good at drawing. If this is the point we're really interested in, as we let this point go closer and closer to the point of interest, our secant will be closer and closer to the actual tangent line. And that's what we're doing. The general position function for a free-falling object, ignoring the air resistance just to make things simpler, is the s equals negative 16t squared plus p sub 0t plus s0. Okay, let's make this an even better one. Here's the one you might see in physics. Now this negative 16 comes from the fact that we live on Earth. But if we were on another planet, that wouldn't be a negative 16. It would still be negative because that refers to what happens because we have gravity. If we're going to be on another planet, we have to make an adjustment. What does it look like? It looks like this, negative, negative 1/2 g squared, gt squared. Notice that this is starting to look like what we had on the left. The part at the end, notice it's another s, but it has s sub 0. The s represents distance. 0 represents before we start our stopwatch, time 0. Where is the object? Because this is distance, so this will tell us where was the object when we started our experiment. The v sub 0 means what was the speed of the object when you started the experiment. G actually represents what's the acceleration due to gravity, where you are. Could write it this way too. Third version. Maybe it's not gravity. This works for any kind of acceleration. The g represents the acceleration due to gravity. So here's the distance that something has traveled. Here's the acceleration that's going under. Here's the velocity when the experiment started. And here's where the object was at the beginning. This will tell us where it is at the end. In fact, if we got more sophisticated or more curious, if the acceleration actually changed, this would be the initial acceleration too. We could make it even bigger or more general. But getting back to the point, here's our formula for what the position is of an object at any particular time t. We're going to assume positive velocities are up. Here we go, positive for up, and negative represent down. Notice up here where I had the G and the A, I had a negative. Where's my, there we go. I had a negative sign in here because gravity works pulling us downward, so it's negative. If we had a different kind of acceleration that pushed us upward, it would be positive. Now if we take the derivative of that, maybe you should have seen this coming. The derivative is negative 32t plus v sub 0. Just a reminder, for s, I'm going to write the s this way, was negative 16t squared plus v sub 0t plus s0. And this one right here, remember, is a constant. It's where the object is starting. So when we take the derivative of this, of course, we've got the s prime, and if we prefer, we could write as ds dt, because it's t that's changing. And we bring that 2 out front, we get negative 32t. And the derivative of t, just like x, is a 1. So we get v sub 0. That's our velocity function. We start with our position function. Take the derivative. We'll just sort of put it this way. Take the derivative, get the velocity function, and if you did it one more time, you'd get the acceleration. So let's get a little bit of a picture going here. I don't know if you've ever done any diving, but here's a picture of someone diving off a diving board. And what we're told is the diving board is 32 feet above the water. So the diver's initial velocity is 16 feet per second. Now if you watch some of those competitions, you'll notice that they don't just drop off usually. They jump up in the air. Well, in this case, it means the person jumped up at 16 feet per second. So where he is, here's our position, S. We can find where he is by putting how much time has gone by in for t in seconds, and do that calculation. Now it asks the question here, when does he hit the water? Okay, what does that mean? Well, when he hits the water, here's the key. When he hits the water, he's 0 feet above the water. Duh, right. You should have gotten that, right? Or maybe not. Not the first time around. So when we take our equation, that means 0 equals negative 16t squared plus 16t plus 32. 0 is how far you are above the water, and you just broke the surface, so there you go. You want to solve it for t? Real simple. Well, not quite so simple. Notice that all three of those numbers can be divisible by 16. So if we divide everything by 16, in fact, notice it's a negative 16t squared. Why don't we divide by negative 16? So what we'll get is 0 equals, remember we're dividing by negative 16, So this becomes a nice clean t squared. Very carefully, you get a minus t, because you divide the 16 by a negative 16, you get a negative 1. Divide the negative 16 into this, you get a negative 2. Be careful about those signs. Now you've got a quadratic. You could throw it in the quadratic formula. You really shouldn't do that, though. You can factor it. T minus 2, t plus 1. Use the zero factor property. Set each of those equal to 0. The first one, if you set t minus 2 equal to 0, you get 2 as your answer. If you set the t plus 1 equal to 0, you get a negative 1. Okay, looks like we might have 2 answers, but what is the question? When does the diver hit the water? Well, we're starting our stopwatch as soon as he takes off from the diving board. The negative 1 doesn't make any sense. We can't go back in time. So our answer is 2 seconds. At 2 seconds, he hits the water. So as soon as he takes off the diving board, hit your stopwatch. Hit your stopwatch again when he breaks the surface of the water. 2 seconds will have gone by. The second question is, how fast is he going when he hits the water? Well, remember, we're at the 2 second point. And what did we say was the velocity function? The velocity function was what? Negative 2. Oops. Let's go back here and look. There we go. Negative 32t plus v0. Negative, let me start this again. His velocity is negative 32t plus (32), is that right? Plus v0. Oops. My mistake. I should have looked back. There we go. Negative 32t plus 16 gives us the diver's velocity at any time at all. We're talking about the 2 second point. That's where he breaks the water. So just to get that, negative 32. You got 2 seconds for the time, and 16. And that comes out to negative 32 feet per second. I should edit that out. That's a good time to use a calculator, right? There we go. That's what I should have done, I guess. So put the 2 in, and there we'll get the answer, negative 48 feet per second. There's our real answer, sorry. So this tells you a story about the diver and how fast and where he is at any particular moment. Now we get this to a little bit of business. Rates of change in economics, we're going to talk about those marginals. Remember, marginal cost, marginal revenue, marginal profit, they all go together. You might also remind yourself that we've got a simple formula which makes logical sense in terms of getting the profit. how much profit do we have? It's the money coming in minus the money going out. What's left? Profit equals revenue minus cost. Keep that in mind. There's the equation that relates those three, and that's total profit, total revenue, total cost. To distinguish them from marginal, marginal, marginal. Here's our marginal profit, and keep in mind that this has to do with calculus, of course. There's our dp dx for marginal profit, dr dx for marginal revenue, and dc dx for marginal cost. You might want to write those down. But after you've used them for a day or two, they'll make total sense, along with the fact that you've got P equals R minus C. So this is an example of what this might look like. There's a function of a discrete variable. Now, there is a class called Discrete Mathematics. Don't be too shocked if you don't know what Discrete Mathematics is. Up until about 20 years ago, I had no idea whatsoever, and I'd taken a bunch of mathematics. If some of you have already taken probability and statistics, you might have run into something that happened to a discrete. Discrete means it comes in individual chunks. If you look at this graph over on the right, you'll notice that the only values of y come at certain places. So, where am I? There we go. Okay. So we've got an x value 0, an x value at 1, an x value at 2, 3, 4. Notice though there's no 6.5. There's no 8.2. There's no 10.385. Only at those individual pieces. So how does that come in with business, for example? Well, here's your business connection. You all know what money is, and if we're talking in dollars just for a moment, even though some of you may have come from other systems, when you're talking about money, for example, let's take something real simple. $1.63. Okay, there's a decimal, but let's simplify it even further, or change it so we write it a different way. This is 163 cents. Now we can buy something or sell something for 163 cents. What we can't do, let me get back on the screen here again, what we can't do is sell something for 16.7 cents. That doesn't make any sense. It comes in chunks of pennies, chunks of cents. Nothing in between. That's what we're talking about when we're talking about discrete values. For example, let's suppose this is supposed to be a die that would throw in some kind of a game. And maybe this side has a 4 on it. To make this sort of dangerous, but okay, there's our die. If we throw the die, what can come up on the top? Our possibilities are, we could get a 1, could get a 2, 3, 4, 5, or 6. Unless you've got an unusual die, those are the only values you're going to get. You will not get a 1.7. So that's an example of discrete values, just like the cents are. If we wanted to simplify things a little bit further, maybe we'd just go by individual dollars and say, we don't care about the cents, let's just stick with the dollars. You could do that too. That's possible. But even if you go down to the cents, you can't have fractions of cents, at least not in the United States. That's what discrete variables are. Now, we usually don't use discrete functions though, but some of our business applications are discrete ones. So that we can use all the mathematics at our disposal. Never mind, there we go. You might say we sort of fake it. Since we've got so many tools that use continuous variables, we can sort of connect the dots and use this as our function and not worry about the fact that some of these in-between values don't make any sense for us. So with that continuity, we can use calculus. Why do we want to do that? Because if we've got an x value, and in our business, remember, always think in terms of some business that you'd really like to be able to do. For that business, the x value represents how many of these things you're selling or buying or fixing or whatever. This represents the number, let's say TV sets, just for example. They might be chairs or something else that you sell. What you'll be interested in as a business person or in management, whatever, is, where am I? There we go. You'll be interested in the marginal revenue, the maximum profit, the minimum cost, and other things. And you usually round the solution to the nearest sensible x value. You don't write, for example, suppose you're trying to find the perfect price to maximize your profit. You and I both know you can't sell something for $1.89, 4, 3, 2, 3. You can't sell something for that. So round to the nearest thing that makes sense. It might be cents, dollars, some kind of units, days. It depends on what the actual context of the problem is. Next. So we've got a formula here and it says the profit from selling X units. So right off the bat, make up something that you're selling. I'm just going to throw TVs in there. Now, for this particular example, maybe the price, won't be like the price for a TV set, whatever. Here's our equation. Someone has gone to the trouble of finding out what the profit function is. There's our profit function. First it says find the marginal profit. Marginal tells you you're going to use calculus. Not only that, you're going to differentiate that profit function. After you do it, then you're going to put 50 units in for the differentiated function. Then you're going to compare the marginal profit with the actual gain in profit. They aren't exactly the same, as you'll see. So first of all, you're going to take that profit function, the profit function we had above. The marginal profit is given by the derivative. Good news, whether you're finding the marginal profit, revenue, or cost, you're going to take the derivative just like we're doing with the profit. So if we take this function above, take the derivative, remember, bring 3 out front. 3 times 0.0002 gives me the 0.006. The x cubed becomes an x squared, and the derivative of 10x is just 10. And there's your marginal profit for whatever number of units you choose. But the question says, what's the marginal profit if we're selling 50 units? So you take that 50, and you're going to put that 50 in where the x is. So your marginal profit another way of writing it, of course, would be like this. And what you're going to do, since you're interested in the 50 unit level, is you're going to put the 50 in where that x is. So you have 0.0006. There goes your 50. If you look at that derivative, or the marginal profit, you're going to square that and add a 10 to it. That'll be your marginal profit. And before we move on to the next slide, well, let's go ahead, move on to the next slide. There's your marginal profit. Do the arithmetic. There's your marginal profit. Add those two together. Now, just a comment before we move on, what does that marginal profit actually mean? Remember that at this point, we were making 50 of these TV sets, or whatever it was, every week, let's say. Marginal profit says if you make one more TV set and sell it, how much more profit are you going to get? That's what marginal profit means. Make one more TV set or whatever it is, how much more profit are you going to get? That's what marginal profit is. You get an additional 11.5 or $11.50 for every extra TV set that you produce. That's marginal profit. And you can adjust that just by changing the words for marginal cost or marginal revenue. So you put the 50 in. The actual profit is $525 when you're selling 50 of those TV sets. Sell 50 of them, that's your profit. You have a good chance of going on a little trip this weekend from that profit. What if you made one more? Well, let's go back. We'll put 51 in instead. If I put 51 in instead, what do we get? We get $536.53. Compare that with what we had before. Remember, at 50 TV sets, this is a reminder, we made $525 of profit. And just now we said At 51, we made $536.53. Things are looking pretty good. If I were a business person, I'd say, let's go for 52. Let's do one more. Notice that the difference between these two, from going to 50 to 51, what's the difference? $11.53. Let me rewrite that. $11.53 is how much extra profit we get for selling that one extra TV set. What did we get a minute ago? Marginal profit was, there we go, $11.50. Not exactly the same. Now the $11.50 is our result by using calculus. So there is a little bit of a difference between the two, but not much. That's the actual extra profit for one unit, $11.53. We approximated it at $11.50, pretty close. And this function that we were playing with, the profit keeps going up as long as the number of units sold goes up. Usually, though, that's not what happens. Usually, if you increase the price, or increase the number of units, something changes. So you have to think about that. Now, here's something new for us. It's the demand function. This might look a little bit strange. To me, it looked strange when I first saw it, because it says this is the demand function, but P represents the price. It's the price per item. If we're selling TV sets, that's the price of each TV set that we sell. And what's it equal to? It's equal to some function of x. So on this side we'll have P for price. On this side we're going to have something that has to do with x. Where's the demand? Well, this x actually represents the demand. Even though it's called the demand function, the x's are on the other side. It might seem a little confusing, but you get used to it after a while. There's the demand function. Remember, it's P equals some function of x. Second, you're going to have to create a revenue function. You've done this already, but just a reminder, the revenue function is x times P. The number of items you're selling times the price of each of those items. It tells you how much money is going to come into your business. So here's an example of a fast food restaurant, and they've determined this is the demand function for this particular fast food restaurant. Notice that on the left is price, and the actual demand is inside the expression on the right-hand side. But it's still called the demand function because the demand is there in the equation. Notice on the graph that as the number of hamburgers are sold goes up, the price goes down, the price that we can sell them for. Here's a table showing you some of the values. If we had a price 0. In other words, we're giving away the hamburgers. We can give them away and get rid of, or sell, if you can call it that, 60,000 hamburgers. If we change the price to 50 cents per hamburger, we can sell 50,000 of them. $1.50 a hamburger, 30,000 can be sold this week. So on down the line, until you get to the point where if you set the price at $3, you're not selling any hamburgers at all. So the question is this: find the increase in revenue per hamburger for monthly sales of 20,000 hamburgers. In other words, find the marginal revenue. So we're going to look for the marginal revenue. So we're going to take the revenue and we're going to differentiate it for x equals 20,000. There's our demand function, and the revenue is given by R equals XP. So revenue equals X, and bring this expression down here. A little bit of algebra, and that's what we've got. Remember, we've taken that 20,000 up here. Where am I? We've taken this 20,000 and brought that out to the front and made that 1 over 20,000, because looking ahead, we're going to have to differentiate, so that's going to help us in the long run. So there's our price function. There's our revenue function. Sorry, it's a little bit on the messy side. There's our revenue. Take the derivative. Pause it if you like with the revenue function back there. So the one you are going to want to use, where am I? So you want to use this version of the revenue function. You're going to take the derivative, and there's your derivative. The reason we brought that 1 over 20,000 out front is we can get that out of the way and just differentiate the rest of it. It makes things a little bit easier. So here's our derivative. And we want the marginal revenue at x equals 20,000. So pull out the x and throw in 20,000. Hit the calculator or do it manually, whatever you like. There's our marginal revenue. That means if we sell or produce one more item, we're going to get $1 more revenue for that production per hamburger. That's important too. Your marginal revenue, marginal cost, or whatever, is the change of that value for each unit of hamburgers or TVs or whatever you're selling. So the cost, they didn't give us this before, but the cost of making X hamburgers or producing them is 5,000 minus 56 cents times X. In other words, each hamburger is costing us 56 cents to make. We've got an overhead of $5,000. Find the profit and marginal profit for each production unit. So we're going to first find out what the profit function is. Then we can differentiate to get the marginal profit. When we get this part right here, Then we'll put the 20,000 in for it, the 24,400 in for it, and the 30,000 in for it to get the marginal profits. So first of all, there's our revenue. We've seen that before. Get the total profit. It's the revenue minus cost. Gives us the profit function. Clean that up a little bit. Differentiate. Our marginal profit is 2.44 minus x over 10,000. So those numbers we wanted to work with before, we'll put those in for x and do the calculations. So for 20,000, put the 20,000 in, and the 24,400, and the 30,000. So profit for the first one is 23,800, and the margin, and for the second one, oops, this isn't working the way I wanted, but you get the point. So just to make sure I get this across right, here's your 20,000, that's how many hamburgers or whatever you've got. You put this into the profit function, evaluate that for an x of 20,000, then you'll take that 20,000 again and you'll put it into the marginal profit function. There's our 20,000 in the marginal profit function. Do our arithmetic. This says that if we increase production by one item, one hamburger or whatever it is, we're going to get 44 cents more per hamburger. For 24,400, it's not working the way I wanted it to. I'm not sure why. I guess I just got extra slides in here I didn't want. So the 24,400 goes in the profit function, and there's your profit. Remember, that's total profit. And there's the marginal profit. Put that in the derivative for x. And, notice that 24,400 units, if you make one more hamburger, you're not making any extra money at all. So you might not want to go over that. So let's see what happens at 30,000. Does it go down, or does it actually go up again? I've got to fix this. Oh, I see what happened. Okay. My apologies. So you take 30,000, that's our third level of production. This is how much profit. You can, if you compare that with what we got in the previous one, you can see the profit's going down. So making 30,000 of them was not a good idea. Put that in for the marginal profit, and you can see you're losing money for every additional item you make. You're losing 56 cents for every extra hamburger that you sell. That doesn't sound like a recipe for success. I'm sorry about the extra slides. Something didn't quite work. I think it's in the animations. And that's it. Okay, that went a bit long, not too bad. But thanks for sticking in there. And you have a good day or a good evening, whatever it is when you're watching this. Bye-bye.